This session gives you an introduction to bowtie analysis and takes you through the basic steps of building a simple bowtie model. To start, let's define what we mean by a hazard. A hazard is something with the potential to cause harm. The thing could be a substance, or an object, or a situation, for example. And the harm could be to people, but also to the environment or to our property or to our company's reputation. So, examples of hazards include a flammable gas or a toxic liquid, or working at height, or driving a car. Bowtie analysis is commonly carried out for a specific hazard. Having determined what hazards exist, in other words by asking what do we have that could cause harm, then one or more hazards can be singled out for bowtie analysis. The bowtie illustrates what happens when we lose control of the hazard. At the centre of the bowtie is the top event. We have lost control and the hazard is released. To build the bowtie, we need to ask, what happens when we lose control of the hazard? So, taking the example of a flammable gas, the centre of the bowtie would look like this. Our hazard, the gas, has been released from its containment and we have lost control of it. Next, we need to ask, how might that loss of control arise, or what might cause that loss of control? In our example, our flammable gas might be released because of overpressurization of the pipework or vessel that normally contains it, or excessive corrosion, or impact damage from a dropped object, for example. There may also be other threats that are not shown here. Our analysis would continue until we've identified all credible threats. Then we need to ask, what happens after control is lost? How does the scenario develop? Our flammable gas might encounter an ignition source resulting in a fire. If the gas ignites in a confined or congested area, we might get an explosion. Again, in reality, there may be more than the two consequences shown here. We now have the basic skeleton of the bowtie diagram, and you can see why it's called a bowtie. The threats on the left side illustrate how control of the hazard can be lost. The loss of control sits in the centre at the knot of the bowtie, and the ultimate consequences, once that initial loss of control has progressed, are shown on the right. It's important to get this basic bowtie framework right. You can check the logic by asking, do these threats lead to this top event, and does this top event result in these consequences? The next step is to ask for each of the causes on the left in turn, how might we prevent this cause from resulting in the top event? For example, how might we prevent overpressure from causing release of the flammable gas? One preventive measure would be to design our vessel or pipeline to an appropriate standard, using the right materials of construction and wall thickness for the operating pressures we expect to see, plus a safety margin. Then we would most likely have in place some form of control system which adjusts the operating parameters to keep the pressure within acceptable limits, with maybe even automatic trips to shut operations down if the pressure rises to too high a level. In reality, there may be more than two controls, and we would continue until we have identified all the controls in place. This process is repeated for each of the causes on the left side of the diagram until you have captured all the preventive measures for your hazard scenario. The right side of the bowtie is populated in a similar way, but this time we ask, Given that we have lost control of the hazard, how might we limit the extent of the consequence? So, for the fire consequence in the example, we would expect to have gas detection systems in place that automatically shut down operations on confirmed gas and therefore reduce the likelihood of ignition. We might also have mitigation measures such as natural or mechanical ventilation, hazardous area classification, etc. If these fail and a fire does occur, we may have firefighting equipment to limit escalation, and we would expect emergency response procedures to be activated to protect personnel from the effects. For an explosion, many of the same mitigation measures apply. But in this case, we might also have buildings which are designed to withstand explosions and therefore protect the people or equipment inside them. We now have a complete Bowtie diagram, with the preventive measures or barriers on the left, and, if the hazard is released, mitigation or recovery measures on the right. We can choose to stop the analysis at this stage, or we can take it to a number of other levels depending on the objectives of our assessment. For example, we quite often want to know whether we have enough barriers for this hazard. How many barriers are enough? When faced with this question, one area to look at is the quality of the barriers. 2 high-quality barriers may be better than 3 or 4 lower-quality ones. So, we can apply a grading system to the barriers to identify which ones are high, medium, or low quality, for example. This is indicated in the diagram by the barrier colours, green being high quality, yellow being medium, and red being poor quality. We could also ask, are there any more barriers that we could add? We have captured what we currently have in place, but could we do anything more? If we identify a potential candidate barrier, we can evaluate the benefit it would bring in terms of risk reduction, and the effort, including the cost, involved in adopting it. Under the ALARP principle, the barrier should be added if the effort involved is not grossly disproportionate to the benefit of adopting it. Another avenue of the analysis that we might choose to develop is to look at the safety critical activities supporting the barriers. Each prevention measure or mitigation measure will only continue to function if it is maintained properly. So, for each box on the diagram, we ask what activity or activities need to be carried out to keep this barrier working. And then we go on to ask who does that activity and how do they know what they have to do. For example, for the measures protecting against dropped object impact, the first barrier requires that the equipment is regularly maintained. A similar safety critical activity will occur anywhere on the Bowtie where there is a barrier that is a piece of equipment. For lifting equipment in particular, there is also another critical activity involving arranging for the equipment to be inspected by a third party. For the second barrier on this branch, for the lifting operation to be controlled effectively, the foreman must conduct a job safety assessment to identify what might go wrong and put controls in place, including the restriction of not lifting over live pressurised plant. He must also carry out a toolbox talk to discuss these controls with the team carrying out the lift. By making this link between Bowtie barriers and the safety critical activities needed to maintain them, we are demonstrating that the prevention and mitigation measures will continue to be effective going forwards. Not only that, but if all the safety critical activities are covered by the organisation's safety management system, which includes the job descriptions which specify who is responsible for doing what, and the procedures and task instructions describing how to carry out these activities, then the safety management system is demonstrably targeted at controlling the organisation's hazards. A final level of analysis that I'd like to explore here involves defining safety critical elements. These are typically defined as items of equipment which act to prevent or mitigate a major accident, or whose failure could result in a major accident. If our Bowtie is depicting a major accident scenario, then by definition, those prevention measures on the left, which are items of equipment, and the mitigation measures on the right, which are items of equipment, are safety critical elements. Once safety critical elements have been identified, the analysis can go on to define, for each element, the standards it must meet in terms of its performance. In other words, what function are we expecting it to perform? How reliable does it have to be? How robust does it need to be? Or how long does it have to survive for? And does it depend on any other elements? The link between each element and its performance standard can be illustrated on the Bowtie. Again, performance standards are part of the management system, and their achievement is checked through performance assurance tasks, usually built into the maintenance management system. They can also be the subject of independent verification. These are just a few of the ways in which Bowtie analysis can be applied to give you a brief introduction to the technique.